System design interviews evaluate the ability to create scalable, robust, and maintainable software systems. The focus is on designing components that can handle growth and complexity while ensuring high performance. Core areas include both low-level and high-level design, where low-level design covers efficient resource utilization and high-level design defines the overall architecture and system interactions. Load balancing is the process of distributing incoming network or application traffic across multiple servers to ensure no single server becomes overwhelmed. This increases availability and responsiveness. Load balancers also monitor server health and route requests to only healthy servers, providing fault tolerance and scalability for handling millions of users efficiently. Distributed database architectures define how data is stored and managed across multiple servers. Common types include client-server, where clients access a central server, peer-to-peer, where nodes share responsibilities equally, federated, integrating independent databases, and shared nothing, which partitions data for horizontal scaling. The choice affects performance, fault tolerance, and complexity. Distributed caching stores frequently access data in multiple cache nodes spread across the system. This reduces database load and improves response times by serving data faster from memory. Key concepts include sharding cache keys across nodes, replicating data for availability, managing cache expiration, and ensuring consistency to avoid stale or out-of-sync data. Sharding is the process of splitting a database into smaller, more manageable pieces called shards. Common sharding methods include key-based sharding, which uses hashing for equal distribution, range-based sharding, dividing data into continuous ranges, vertical sharding, separating tables or columns, and directory-based sharding, using a lookup service. Sharding helps scale databases horizontally and improves performance. Replication involves copying and maintaining database copies in multiple locations to improve availability and fault tolerance. Popular replication models include master-slave, where one node handles writes and others read, multi-master, allowing writes on multiple nodes, and peer-to-peer, where all nodes are equal peers. Replication ensures data durability and supports disaster recovery. Cache eviction policies determine which data to remove from the cache when space is needed. Common policies are least recently used, which evicts data accessed longest ago, least frequently used, removing data used least often, first in first out, evicting oldest entries, and random replacement, removing data randomly. Choosing an effective policy is critical for maintaining cache efficiency. Optimizing database queries improves system performance and reduces latency. Techniques include using indexes properly, avoiding selecting unnecessary columns, optimizing joins by indexing foreign keys, minimizing subqueries, using appropriate data types to speed comparisons, caching frequent queries, and analyzing query execution plans. Efficient queries reduce server load and enhance user experience. Securing databases involves several best practices to protect sensitive data. These include isolating database servers from application servers, enforcing strong authentication and access controls, encrypting data both at rest and in transit, regularly applying security patches, and monitoring database activity to detect suspicious behavior. Proper security measures mitigate risks of unauthorized access and data breaches. Effective backup and recovery strategies are essential to protect against data loss. Follow the 3-2-1 rule. Keep 3 copies of data on 2 different storage mediums, with 1 copy stored offsite. Automate regular backups, protect backups using encryption, and routinely test recovery processes to verify data integrity. Strong backup plans reduce downtime and minimize data loss during failures. Database performance monitoring involves tracking key metrics like query latency, CPU and memory usage, and throughput using tools such as SolarWinds, Datadog, or Prometheus. Monitoring provides real-time alerts and historical data that help identify slow queries and resource bottlenecks. Continuous monitoring is vital for maintaining database health and ensuring application responsiveness. Disaster recovery planning prepares organizations to respond effectively to catastrophic events. It involves identifying critical systems, defining recovery time and point objectives, creating response procedures, establishing communication plans, and conducting regular tests. A comprehensive disaster recovery plan ensures business continuity by minimizing downtime during failures or disasters.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.